Hi, welcome to the Signal Path. I have a teardown and analysis video for you guys of something that you probably haven't seen a teardown of before. This is an Agilent N2802A. This is an InfiniMax III probe, and it has 25 gigahertz of analog bandwidth, about 17 picoseconds of rise time. Now, these probes are often used for making differential measurements on high data rate backplane drivers, as well as optical communication. And this system of probes, the InfiniMax III, actually goes all the way to just above 30 gigahertz of bandwidth. And these are compatible with the X-Series oscilloscopes, the oscilloscopes that of course have sufficient bandwidth to take advantage of. Now, if you look at one of my old videos, I did a review, an experiment video of one of the X-Series oscilloscopes, the one that has two channels at 62 gigahertz, is 160 gigasample per second oscilloscope. I highly recommend that you watch that. There's quite a bit of information about what goes on to make an oscilloscope like that. And that actually uses a down-convert mixer to convert into two bands of 33 gigahertz, and then uses two 80 gigasample per seconds to sample those 33 gigahertz bandwidths with some overlap, and then doing correction, correlation, cancellation, and so on to get a total of 62 gigahertz of bandwidth. Now, the interesting thing is that the front-end amplifier of that oscilloscope uses an in-house indium phosphide technology from Keysight, which I think is now at least a half a terahertz FT process. And that amplifier design and that process is the ASIC that is in the front-end amplifier of this probe. So it should be very interesting to do a teardown of this section, which is the amplifier section. Now, this is a broken probe. I picked this up from eBay for $170, not with the intention of fixing it, because these things aren't repairable once they're broken, because once the ASIC is dead, it's basically a done deal. And this one presents itself as a large DC offset when you plug it into the unit, which is a very classic sign of the fact that the front-end amplifier is dead. So anyway, I don't even have an X-Series oscilloscope here in my lab to continue to work on it, even if I wanted to. So I just bought it, paid $170 or so just to make this video. I thought it would be very interesting to take it apart. Now, these things can accept up to plus and minus 18 volt of DC voltage. So they are hard to kill that way, but they can only take a 5 volt of AC. And of course, they are EST sensitive. So I'm not sure how this one had died. The person who sold it didn't know, but it's definitely not working other than that. Now, all the InfiniMax III series probes from Keysight, which offers one of the broadest range of accessories that I think on the market, as well as the highest bandwidth, they all have the same interface, and they can connect all to the front-end amplifier. And you can see there's a light switch here, and if you have the browser head, then you can actually turn the light on, see what you're doing. Very, very sophisticated bunch of stuff. I have shown an active probe at lower frequency when I was doing the review of the S-Series scope, but this obviously has a different mount, so you cannot connect that to it. You can even connect this to a spectrum analyzer with the proper adapter, which then powers the whole thing. Now, the other thing is that the input impedance of this front-end amplifier is about 100 kilo ohm at DC and about 10 kilo ohm at very high frequencies. It only has 32 femtofarad of differential input capacitance, and it's a 6-to-1 probe. Of course, it's going to have attenuation. It's almost impossible not to have that if you're going to have high impedance into 50 ohm. Of course, the interface here is 50 ohm. So I thought for taking it apart, we will start with taking this portion just to see the electronic interface, and then go ahead and take a look at this module here, and we'll have to probably look at it under the microscope in order to see all the different sections and try and do some reverse engineering. It should be very cool to look inside this and see the amplifier. Now, as far as I can tell, this is not hermetically sealed, which is a little bit interesting. I guess they can go ahead and not hermetically seal this portion, even though it has 3.5 technologies in it, and I think it's possible to do 3.5 like that. I'd be curious to take a look. But anyway, let's go ahead and start with this guy, take it apart, and see what's going on in it. Should be very cool to see. By the way, one thing I think I forgot to mention, is that these probes cost $23,500. They're not cheap, and most of the cost of that is from obviously the research and development of creating something like this, but also the indium phosphide front-end amplifier has really low yield, and I'm sure they make many of them before they have some of them that have the specification that they're looking for. That's one of the reasons why they're expensive. Now, Keysight doesn't really repair these, even though I paid $100 something for this. I can't give it to them to repair it, because they still ask, they basically scrap it and give you another one, because they know this is not something that they want to spend time repairing on, and they charge about half the price of what it's for. So it's going to be about $11,000 repair. Is just not worth it for me, especially since I can't even connect it to anything. So I just wanted to give you an idea that these things are very, very pricey. That's probably why you haven't seen a teardown one of these, because they're so expensive, but this is a great opportunity. So let's go. Alright, here we go, a couple of screws. I should be able to open this carefully, even though it's broken. Ah, look at that. That is pretty. Let's see. Let me just put this down in a way where I can easily focus on this. Here we go. There we go. That looks nice. Now, immediately, we can recognize the different components. Let me find my pointing tool here. Here we go. Now obviously the main signal that's coming in is going to have to be through a coax, and a coax being able to handle 25 gigahertz. And ultimately here you can see connected to this converter here that has probably a K connector on one side. And I will be able to disconnect this and separate it. Now through this cable they also have to run a bunch of other cables which will provide power and signals and other things to the front end amplifier, and those are these cables that you can see right here. And on the PCB you might be able to see just over there that they have labeled all the colors of where these cables have to fit in. This flexible ribbon cable is the one that goes onto the little PCB here, which makes contact to the front of the oscilloscope's connector, and everything else is pretty straightforward. Here are the buttons. You can see I can press them like that, and they are the buttons that connect to this. Now this is a die cast, a very nice piece. You can see all custom, obviously. A lot of designs going through these, and all the light pipes then lead light into the different components for the operation and calibration warning, high gain and normal gain, sensitivity settings, and so on. And I can see a bunch of connectors in here, most likely to download calibration coefficients for this specific probe, because these are individually measured, the frequency response, and corrected for, and I think that's stored all in here, so that when you plug it into the scope it will download this, because there's no way to get 25 gigahertz flat bandwidth over all the different dies, especially from a 3.5 technology, and they correct for that to give you the proper amplitude flatness that you're looking for. Now look at that and see what this analog device part actually is. But very straightforward, otherwise there's not much in here. This DC connector that you see here is the common mode voltage, which you can set externally or internally by programming it directly into here. So this might actually be a DAC, I have to look, and that way you can put in any common mode voltage that you like on the input of the probe in order to make it compatible with the current, with the voltage that is on the bus, so that you don't have current being drawn in and out and so on. You can compensate for DC voltages that you're trying to measure. So pretty straightforward, and I think this should be able to be taken off further. There we go. There it is, and that comes out. And you can see that I can separate this. I'd like to get this PCB out, and I think actually I might be able to. Sorry, the camera is really in the way here, so you have to excuse the clumsiness here. There we go. Let's see what's on the other side of this. There it is. Yeah, so just to be as we expect, we're going to find some crystals and some processors, because this thing has its own functions, and it has a whole bunch of interface things that it can handle, biasing and doing all the, like I said, the calibration coefficients, as well as the interface to the oscilloscope, which I think is I2C, if I'm not mistaken. So we can take a quick look at these components, and I'll tell you exactly what each of them is. And obviously there's something here that must have been programmed. So this definitely is the programming port, as well as downloading all the coefficients directly into this, or they may just be programming it and then download the coefficients through the scope interface. I am not sure, but let me tell you what these components are. So here's the connector. I took it off, and then just as I said, it has a K connector at the one end and the probe interface on the other end, and I bet this connector itself is worth more than $170. These things are really pricey, especially from good manufacturers. And here's the main board, and this is where the connector I just showed you was connected to. So now it's, I've removed that, and also removed the ribbon cable. And you can see the ribbon cable right here. I'm not sure how the camera will try and focus on this, but you can see that they have a little piece of come on, this thing can focus. There it is. There's a piece of PCB there where the ribbon cable is glued on top of, and you can see the individual contact points coming from the front of the scope. That has a I2C interface, as well as of course provides power to the probe. Now the other things I wanted to point out, just as I thought, this is indeed a DAC. It's a 14-bit DAC from Analog Devices, which does the biasing, I believe, for a whole bunch of things, not just for the input, but it handles a couple of different biasing points on the board as well. And this is a serial EEPROM. That's likely where the calibration constants are stored. This is a precision op amp there. You can see its proximity to the connector, obviously for some biasing of the front end amplifier. Now if I flip it to the other side, and here, this is a 500 milliamp high current op amp, definitely again for biasing for the indium phosphide front end. Those 3.5 technology ASICs require quite a bit of different biasing, and also in order to characterize them, in order to put them at the optimum operating, and it's going to be different between each die and so on. It's just a nightmare. Anyhow, that's one of these components for that. This is the 20 megahertz clock oscillator. This is a CMOS switch. I forget what this was. I believe this was another op amp. And here we have a PIC microcontroller, PIC 18F877 or 16F877. One of my favorite PICs. Actually, I've used this one quite a lot. I was a little bit surprised to find that one over here. But you can see the design is pretty straightforward. What you would expect is exactly what we see here: a processor to handle all the communication between this to the scope, to read the calibration data, upload the calibration data, optimize a bias the front-end amplifier exactly where it needs to be biased, the DACs on there, you know, put a high current op amp there to provide a bias current to the front end. So very predictable, exactly like what I was saying it's going to look like. That's, you know, what it is, pretty straightforward. Obviously this is not where the cost is. These are pretty straightforward. You're not paying $23,000 for this. You're paying it for the front end as well as the connectors, interface, and research and development, and so on. So I think this is a pretty good look at this portion. I'm sure you're all waiting excitedly to see what's in here. And you can see, and if I take this off, I don't know why they put this on for something that's dead. You can see the special connectors that are there, and this will interface to a variety of different heads. And this pin that you see here, if I'm not mistaken, I believe is where the current will come in to turn the light, which you can have if the different browser will have a light attachment, and the ground return will be the ground of the microwave ground that's connected to the bits. And you can see the body of the chassis that is used to house the front end amplifier. So now we're gonna take this apart and take a look. It should be cool. One other little thing, this is of course the 25 gigahertz coax that goes through and has other cables wrapped around it, but you can see that they have a metal piece here which protects the edge of the plastic edge of this cable against the metal edge of the chassis at the end. So they've really thought this through to improve the life of this component, because you know you don't want to spend $23,500 for something and like this cable is going to get cut because you're bending it and moving it around. So they've thought about making this as robust as they can. Now I don't know much about the failure rate of these. I know that they're quite sensitive to dying if you misuse them, but I'm not sure how many of them fail due to mechanical failure. This one was in great shape, even though it's quite old, I believe, and it still works. What must have been working mechanically quite well. Someone just destroyed the front end amplifier. So let's go ahead and see if this can be taken apart. And I have already done a little bit of wiggling on this. I think I've gotten it. There we go. There it is. That's the top cover. And there you go. It's definitely not hermetically sealed. There's a hole right there in the middle. Oh, there you go. There comes the bottom. Ah, look at that. Here is the cable that I was talking about that goes through here to that front end connector. I'm pretty sure that's for the light. And anyhow, that's going to be there. I don't know what to do with it, whether I should take it off or not. And let me see. This thing actually seems like it will slide out of the way if it's not caught onto anything. There we go. There it is. You know, I have to say I was just praising this thing's mechanical integrity, but I'm not sure how good the mechanical integrity of this piece is. It seems pretty loose actually. So I don't know why they haven't gone through the trouble of doing the same thing, having a metal insert here to improve how hard this is, because this I guess this piece here will provide some protection, but this connection is fairly loose. And yeah, you can see this is obviously all put together by hand. Someone has done this by hand here. So I'm not sure if I want to take these cables apart. I don't think these cables really will tell us anything. What we want to see is what's inside this can. And from what I can tell, I think this should be actually pretty straightforward to open. Now the camera is in the way here for me. Oh yeah, definitely easy to open. Yeah, there we go. Now I don't want this to slide inside the module and then destroy everything. So I have to be very, very careful here. There we go. Yeah, we're almost there. You know what? I'm gonna have to do this away from the camera because I'm pretty sure with the camera in the way I'm gonna destroy it. And here we go. I think this is the world first teardown of this. I don't know, is it? I wonder. I didn't do a search to find out. And there it is. Look at it. It is so pretty. Now, that blue color that you see is a type of dielectric, thermal as well as high low dielectric loss material that Keysight created when they made the A to D converters for the X-Series oscilloscopes. And this is something that they talked about, I remember, and you can obviously see that they're using the same material here. Now, you cannot tell much obviously by looking at it in the camera. We're going to have to look at it under the microscope, but you can see the big decoupling caps and all the bias and circuitry here and here, and the traces going in. Here's the two inputs. You can see that they come in through the package and they go into the main ASIC in the center. There's a couple of more circuits in the middle, probably for biasing and so on. I have to take a look under the microscope, and there's a Micro-Coax that goes from the output of that, which is now single-ended, directly to the oscilloscope. So pretty neat. Time to put this under the microscope. And here we have the probe directly under the microscope, and there's a lot that we can see going on here. Obviously the input biasing, the DC input biasing of the whole front-end amplifier is provided with these signals right here. Now these signals are going to be responsible for setting the DC common mode input voltage range, as well as the voltage that appears at the input of the probe in order to compensate for single-ended measurements and so on, so you can cancel any DC bias that you have on your lines, on your buses that you're trying to measure. So you can see some big decoupling caps, big compared to everything else of course, and you can even see one decoupling cap here which seems to be DQ'd with a resistor and another parallel capacitor in parallel to perhaps DQ it further or to create the necessary time constant. Now these black spots are likely all resistors. In the center you see the main indium phosphide chip, which is the main amplifier. It's a differential in, differential out amplifier, but clearly one side of it is terminated to 50 ohms, while the other side is going through first a small piece of microstrip transmission line and then goes into a Micro-Coax, which is built into this module. Interestingly enough, it seems like they inject these blue dielectric material directly into the Micro-Coax as well, perhaps a very low loss dielectric constant material, as I was saying before, to create a very broadband, well-matched low-loss Micro-Coax line directly in the package. This is clearly something they've developed and quite expensive to produce these. Pretty cool to see here that you can see the blue material is filling inside the tube here, and everything also is pretty straightforward. All the biasing of the indium phosphide chip clearly comes from here. Everything is wire bonded, double wire bonded on the 25 GHz inputs and outputs, as to be expected on something for this frequency range. Then we have the input to the probe is up here, positive and negative down here, and you can see that they both come in through microstrip transmission lines, and look, they seem to be AC coupled first before they go to the input of the indium phosphide chip. But this is actually a two-path. To me, it looks like this is a two-path, a high-speed path and a lowest-speed path. The lowest speed path, which is the biasing of the probe, comes through here, through this whole bunch of circuitry, which then biases the input common mode voltage of the indium phosphide chipsets. And you can do this by creating this two-path and compensate the frequency response and all that, in order to AC couple the input of the indium phosphide chip so that it doesn't have to see the large range of voltages. Only these circuits have to process the large DC voltage that are at the input of this probe. Pretty interesting. At least this is what I think is happening based on what I'm seeing here, and you can see the resistors here biasing the input of the indium phosphide chip. Everything else is pretty straightforward. They're just biasing, and you can see the chassis is of course nice, big ground, everything is shielded. This is not hermetically sealed, and I don't believe the chips are covered with anything. So pretty cool to see. And I'm not sure what technology this is made in. By the look of it, I would say either an old SIGI or a CMOS process. There's a couple of other little ASICs there, but nothing major. But clearly all the magic is in this indium phosphide chip in the front here. Now I'm going to zoom in a little bit more in here, see if you can find any of the details of the ICs, but I don't think we're going to be able to see much with my microscope. You need to put it under a much higher proper optical microscope to see the details. But I don't think this is a distributed amplifier. I think it's just a basic amplifier. Maybe we can see that if it is distributed, we should be able to see it if you look closer. But yeah, pretty cool. I think what I'm saying is correct. If you know more about it, let me know. But I do believe that this is a two-path, two different types of signals going in. Pretty cool to see the operation. So let's take a closer look over here and see if we can discover any more detail. And here we go, a closer look. Now you can clearly see what's going on here. Here's the biasing input resistors to the indium phosphide chip right here, double wire bonds as I was saying. Here's the termination. And looking at this, again, I can't see the detail. It doesn't look like it's a distributed amplifier. I would have loved to see how they, what's going on in here. But again, I mean, making a 25 gigahertz amplifier is really quite trivial now. It's not very difficult. But of course here they have an advantage of having a very low noise and very high breakdown from the indium phosphide devices here. So that's definitely an advantage, which is why they've chosen to go in this direction. This chip seems to have much finer lithography. Probably, I don't think it's an indium phosphide anymore, but interesting nonetheless to see. Like I said, I believe these are decoupling caps, and so you have this two-path solution going on. But you can also see the blue material. You can see the input of this Micro-Coax here directly being fed with this microstrip transmission line. Decoupling caps more close by to the IC. You can see the bottom of the IC, which is the ground where the IC is sitting on, decoupled to these lines. All microwave design. Interesting here is probably for probing. Yeah, I'm pretty sure that's what this is. They can probe the IC here to do some testing, perhaps to chase something. I wonder if they have a secondary path output, although I doubt it. But pretty cool to see. I would love to see the schematic. Some more resistors here for biasing and wire bonds everywhere. Interesting design here with the crisscrossing. I wonder why they've done that. There's a couple of different reasons why they might have chosen to do this for symmetry and so on, but pretty interesting. Anyhow, if you guys have any more information on this, I would love to see it. Just again, I'm just looking at it for a few minutes myself. I haven't spent a lot of time. I like to do these videos kind of live so that my thought process goes into the video, even if there is sometimes something that I might be missing, so it would create an interesting conversation later on. So I think this is a fairly quick video, but nonetheless I think something that probably haven't seen before. So if you like it, leave a comment, rate the video, and ask some questions, and it's always interesting to see the discussions going on. I hope you like this. Until next time.